All right, let's jump right into this explainer and tackle what is, honestly, a notoriously tricky algorithm problem. I mean, if you've ever stared down LeetCode number 10 and just wondered how to approach it without your code spiraling into some endless, messy loop, well, you're in the right place. We are going to break the whole thing down step by step. Right out of the gate, take a look at the problem prompt. We need to match an entire input string to a given pattern, and we have to use specific rules for dots and stars. Now, the absolute keyword here is entire. We aren't just looking for a tiny partial match hidden somewhere inside a string. No, the pattern has to account for every single character from start to finish. And both the string and the pattern will only be lowercase English letters, plus those two tricky special characters we just mentioned. So here's our roadmap for the explainer. 1. The matching problem. 2. The problem with stars. 3. Dynamic programming setup. 4. Defining the rules. And 5. Step-by-step solution. Let's kick things off with section 1, the matching problem. Now, the entire algorithm really hinges on making absolutely sure we have a rock-solid grasp of how those two special characters behave. First up, the dot. This one's pretty straightforward, honestly. Think of it as a universal single-character placeholder. If your string has an A, a B, or, say, a Z, and your pattern has a dot in that exact same position, boom, it's a guaranteed match for that one space. It acts exactly like any other character. It just politely agrees to be whatever letter happens to be standing right across from it. But then we get to the star. Now look closely at this definition, because it is absolutely not your standard glob wildcard. This is literally where almost everyone gets tripped up. Instead of just matching anything, it acts more like a multiplier for the character immediately preceding it. So it can multiply that preceding character by 1, by 50, or, and this is incredibly crucial, by 0, which effectively makes that preceding character completely disappear. Which brings us right into section 2, the problem with stars. Let's look at why that little star character causes us so many headaches when we actually sit down to write the code. Okay, so if you try to brute force this with a naive iterative loop, just checking it character by character, you are going to hit a wall, for sure. Imagine trying to match the string AAB with the pattern C star A star. Your loop sees the A and the string and the C and the pattern and immediately thinks, nope, fail. But wait, that C is followed by a star, which means we could actually choose to have 0 Cs. To solve this with a simple loop, you'd basically have to create this massive branching decision tree that tries guessing every single possible star combination. It's incredibly inefficient. And that is exactly why we need to bring in the hero of our explainer, dynamic programming. Moving into section 3, dynamic programming setup. Let's get our framework established. All right, we're going to visualize this as a 2D Boolean grid. Notice how we've placed our target string, AAB, right on the y-axis, and our pattern, C star A star B, along the x-axis. But look closely at the edges. We've actually added an extra row at the very top and an extra column on the far left. These represent an empty string and an empty pattern. This right here is an absolutely essential trick in dynamic programming because it gives us a foundation, our base cases, to build upon before we even look at a single actual letter. So before we let the algorithm run wild, we actually have to populate those base cases. Now, an empty string perfectly matches an empty pattern, right? So that gives us a true starting anchor at the very top left, cell 00. But what if the string is empty and the pattern is C star? Well, because the star can mean 0 occurrences of C, C star actually can perfectly match an empty string. We program this by telling the matrix to just look 2 columns to the left. If that cell 2 spaces back is true, then our current star cell is also true. And that leads us to section 4, defining the rules. Before we start filling in the rest of the board, we need to know the mechanics. The recurrence relation basically gives us 3 very clear paths. Step 1. If the characters match exactly, or if the pattern has a dot, we simply pull the value diagonally from the top left cell. Step 2. If we hit a star, our first option is to treat it as 0 occurrences. To do this, we just look 2 columns to the left, exactly like we did in the base cases. Step 3. If we hit a star and the preceding character actually matches our current string character, we can treat it as 1 or more occurrences. In that specific case, we just pull the value straight down from the row directly above it. Let's put it all together. In section 5, step-by-step solution. We're going to step right through our example string AAB against the pattern C star A star B. Starting way up in that first row, we're comparing an empty string against our pattern. When we hit the pattern C star, well, as we just discussed, it evaluates to true because the star lets us select 0 occurrences of that preceding C. So we pull that true value from 2 columns to the left. The rest of the row, however, evaluates to false simply because we eventually run out of stars to cancel out the letters. Now, let's move down to the first A in our string. It completely ignores the C and the star, just looking left. But when it evaluates against the A in the pattern, boom, they match exactly. Following our rules for an exact match, we pull the true value diagonally from the top left, which just so happens to be our base case true. So this cell becomes true.
Okay, let's look at the second A in our string AB. When this A encounters the star in the C star pattern, it checks the preceding character, which is an A. They match. This means our logic branch has successfully matched one or more occurrences. So according to rule number 3, we just carry the true value straight down from the row above.
And from there, we just continue this simple, repetitive process. We're checking for a direct match, checking 2 columns left for a 0 star, or checking the row above for a multiple star. Following those rules all the way down to the bottom right corner, our final cell, evaluating the B against the B, pulls diagonally from the true cell we just established. So our final answer is true. This proves the full string perfectly matches the pattern, and we did it without any messy backtracking or endless recursive loops. So what does this all mean? Why go through all this trouble? Well, by caching these subproblems inside our matrix, we've successfully reduced a massive exponential decision tree problem down to a highly efficient big O of m times n time and space complexity. To put that into perspective, m and n are just the lengths of our string and pattern. We literally only ever have to calculate each cell exactly once. It's a real game changer. Now, I'll leave you with this final thought to ponder. We've totally solved the time complexity, but look really closely at how those rules actually work. Notice how we only ever look at the current row and the previous row. Ask yourself, do you really need to keep the entire 2D matrix in memory all at once? Or could you optimize your code to just use a couple of 1D arrays? Think about it. Thanks for working through this explainer with me, and happy coding.